All right, for two-dimensional vectors, we're talking about vectors in a plane, with x and y coordinates, or two coordinates anyway. You don't have to call them x and y. And when working in two dimensions, the basic rules that we've learned for vectors so far still apply. You can still add or subtract vectors, but it's more complicated than it is in one dimension because now the vectors don't necessarily have to be heading either in exactly the same or exactly the opposite directions. So that complicates things a bit. And you can multiply or divide vectors by scalars. And you can use unit vectors and all that nice stuff here also. Not as simple as I mentioned a moment ago, not as simple as one-dimensional problems, but why would it be? It's got two dimensions. In effect, what you have to do to solve the problems is use geometry to find the resultant or the difference. And trigonometry to find the magnitude and direction. And this is a lot like navigation. In the old days, before we had computerized programs for that sort of thing, airline pilots or ship captains would have to sit down with maps and sort of draw out their course using vectors. And it's very similar to what we do here when we use the geometric method for adding or subtracting vectors. For the geometric method, there are other methods which we will actually spend more time on. I'm going to introduce the geometric method and show maybe a couple simple examples. We don't use the graphic, that is the geometric method, too often because it's not as accurate as using the more mathematical methods. Solving vectors geometrically is fairly complicated. Well, maybe not exactly complicated, but it requires a lot of very precise work. For one thing, it requires a couple of rulers, a triangle, and a protractor. And that's the minimum that it requires. And even if you're very careful with it, there are mathematical methods that are still more accurate. So I'm not going to do a whole lot with the geometric method. But anyway, for the geometric method, what we do is we use what's known as the parallelogram rule to find the resultant. That is, if you have two vectors that are at an angle to each other, you can basically draw lines, like dotted pencil lines that are parallel to those two vectors and of the same magnitude, and basically turn those two vectors into a parallelogram, and then the diagonal of the parallelogram will be the resultant of the vectors. So, for example, say you have vectors A and B, and vector A is of this magnitude and pointing in that direction, and vector B is of this magnitude and pointing in this direction. So what you want to do is translate either vector, that is, in other words, move it while maintaining its magnitude and orientation. Um, it doesn't matter which vector you move, but you want to get it so that the origin points are the same. And so for these two vectors, we would have, something like this. And I'm trying really hard to get these the same magnitude and direction. That's kind of sort of close. Okay, so that's not too bad. Obviously, if you want an accurate answer, you're going to have to be much more accurate in doing these things than I'm being right now. And you have something like this, and then step 3, from the end or the point of vector A, you want to draw a line parallel to vector B of the same magnitude as B. And then you do the same thing, only with the names reversed. So if we have, from the end of vector A, we want to draw a line parallel to B, which is of the same magnitude as B. I keep wanting to curve it. That still looks like it gets closer. Yeah, okay, I guess that's pretty good. This is not a vector you're drawing, so you don't need an arrow at the end of it. Okay, so you'd want to measure this if you're doing it carefully, of course, to make sure that the length of this line is the same as the length of B. And then you do the same thing from B. The head of B, you draw a line parallel to vector A and of the same magnitude as vector A. So you end up with something like that. Okay, and so basically what we have here is the resultant will be the diagonal, basically the longer diagonal. Basically from the origins to the opposite corner. So the resultant will be this line here. So the resultant will be the longer of the two diagonals of this parallelogram because you're adding them. So if you're adding the vectors, it'll be the longer diagonal. In other words, the diagonal that starts at the origins and goes to the opposite corner. And in this situation, you'll notice that vector r equals vector a plus vector b. So this is the resultant. It's equal to the sum of vector a and vector b. That's only when you consider both magnitude and direction, though. The magnitude alone is not equal to a plus b. If you basically measure this, the length of the resultant, you'll find that it's actually less than the total of b plus a. Okay, so the magnitudes do not add up. And that's one of the complications when you're dealing in two dimensions. Things that aren't exactly parallel or anti-parallel to each other. And another thing you might notice is that there's another diagonal to this parallelogram. And that would be the difference between A and B. If we had, let me look at them just to see how I drew them. Say A and negative B, that is a vector of the same length but pointing in the opposite direction. We could put them together like this. Again, translate them so that their origins overlap. And what we have here would be essentially what you do is the same thing we did before. So you end up with B and A with their origins overlapping. For B, you basically have to reverse it and make it point the other way so that you can get the origins to overlap like this. And you can draw the other lines to make the parallelogram. And this time it's the yeah, okay, that's the right one. It's the sorry, the vector that goes from the end of one vector to the other. So vector D, the difference is simply equal to vector A minus vector B. But again, the magnitudes don't work that way. Okay. To find the magnitudes, we need to use trigonometric laws. For triangles. That is, obviously, if you're being really careful and drawing this out on graph paper and being sure that you're getting the lengths exactly right and getting the angles exactly right, then you can just measure the length of the resultant or the difference vectors, and you get a fairly accurate reading on what their magnitudes are from that. But there are better ways to do it. And so one of them would be trigonometric laws for triangles. That gets pretty complicated. So we might be interested in alternatives. Well, one alternative would be vector components. And we'll cover that a little bit later. The one we're going to look at right now is drawing the vectors to scale. In other words, the geometric approach, where you have to be really careful, and even so, the answer you get is probably not going to be as accurate as you would get by using components. But we'll take a quick look anyway at actually drawing it to scale. So this is basically doing it on paper. And as I said, this method requires a lot of care. You have to be very careful to be very accurate, and it's still not as accurate as trigonometry or components. So in the end, our favored method for doing stuff like this is going to end up being components. A little foreshadowing there. If you're adding or subtracting, multiple vectors, and by multiple I just mean more than two, then what you can do is repeat the parallelogram rule over and over again. So you take basically the first two vectors, use the parallelogram rule to find the resultant of that, and basically then you find the resultant of all the resultants. So for example, if you had three vectors that you had to add up, you could find the resultant of vector 1 and vector 2. Then you need to find the resultant of the first resultant with vector 3. So for each successive pair of vectors, you find the resultant of that pair, then you find the resultant of that resultant and the next vector, then that resultant and the next vector, until finally you're done. And that the last resultant should be the overall resultant for the whole thing. And the order in which you do that shouldn't matter, because again, adding of vectors is commutative and associative. And like I think I mentioned before, if you're graphing it out on paper, doing it in different order might result in different looking shapes being mapped out on the paper. but in the end, the magnitude and direction of the resultant should end up being the same. As an example of travel in Florida, I'm going to start a new page for that because it takes up some space. For travel in Florida, the book goes through all kinds of stuff on who you're going to see and why you're going from one place to another. But I'll just say you're going from Tallahassee to Jacksonville to Daytona Beach to Orlando to Tampa to Gainesville. And you can represent the legs of the trip by designating them as, you say D1, D2, D3, like we did before, or vector A, B, C, D, and E. And then the question is, what is the total displacement when you reach Gainesville? Well, if you have the map, actually, if you look at the map that they provide in the textbook, I'm not sure why you wouldn't just take your ruler and measure the distance from Tallahassee straight to Gainesville, because that's your final displacement. But if you're not being given the map, basically, if you're being given the distances and directions of each city relative to the last one, then you would basically have to map it out like they do in the figure in the book, only you wouldn't have the map to do it on. You'd have to draw it more or less freehand on some graph paper using the protractor and everything to make sure you get all the angles just right. Essentially, it ends up looking something like this. You can look at the diagram in the book to see it accurately, but if you're drawing it by hand, it might go something like this. So segment A, and then segment B, and then segment C, and then segment D, and then segment E. And the resultant, of course, like I said, will be straight from the origin of the first vector to the end of the last vector. So there's your R. If it's done on a map, then like I said, all you basically have to do is connect the dots for each of the cities and then measure this. But again, if you're just given distances and directions, then you'd have to draw it more like freehand. And essentially, if you were drawing it freehand, or with the aid of rulers and protractors, that is, you can do a couple of things. You can use the parallelogram rule 4 times. So use it for A and B, find that resultant, then find the resultant between the first resultant and C. Take that resultant and find the resultant between that and D, and then take that resultant and find the resultant with E, and you should be done. Or, of course, as I said, you can just measure the magnitude and direction of vector R, but that assumes that the other vectors have been drawn very accurately. So that would take a lot of care in order to do that. In general, to find the resultant of multiple vectors, you can draw the vectors head to tail, maintaining lengths and directions. Then you can draw the resultant vector and that would go from the origin of the first vector you put on paper to the point or the tip or the end of the last vector that you drew. And you can measure its magnitude and direction. And as I said, the order of the drawing of the vectors shouldn't matter. Although, you may get different looking shapes on the paper, so you may not end up with a shape that looks like this. The important thing is that R will be this length and it will be heading in this direction, no matter what order you do these other vectors in. Okay, so that brings us to components of a vector, which we don't have time for right now, but we'll get to that, I guess, in our in-person lecture next week. So see you then.